Thank you for joining our high-level overview as we present the latest ISO 26262 standard and how it may be impacting your business. It is a pleasure to take this opportunity and offer knowledge tidbits for you. In appreciation for your attendance, you will be emailed a 5% off discount code for one of our 5-day TUV Nord certification courses this year. After the webinar, you will be emailed the slide deck used today. Upon entering the webinar, your microphone is automatically muted. If you have questions during the presentation, we would love to talk with you. The final slide lists LHP representatives who can either answer you directly or connect you with the appropriate resource. Thank you for learning with us. I am Pamela Tart and serve as the Director of Corporate Training for LHP Engineering Solutions, based in Columbus, Indiana. Our Solutions Architect for Automotive Functional Safety is Victor Aguilar, and he will present for you shortly. As we walk you through our presentation, be thinking about your organization. How is it structured, and what improvements may need to be implemented to achieve compliancy? And instead of me getting tongue-tied referencing all those 2s and all those 6s, I will instead refer to it simply as the standard. But first, let's take a few minutes and review LHP as a company and our expertise in the automotive industry. For those of you who are new to LHP, our company lives in the automotive sector, providing embedded engineering services in the form of project consultation, high-talent engineering resourcing, big data services, and both technical and non-technical training. The LHP ecosystem is comprised of leading-edge technologies. With the rapid changes taking place in the automotive industry, our experts provide services covering the entire engineering V diagram. We are a solutions provider from concept to production. LHP is a global company with its headquarters based in Columbus, Indiana, and several locations across the globe, spanning 3 continents and multiple industries. We are almost 20 years old and have a vast array of customers. Our North American customer base ranges from automotive to renewable energies, government entities to companies publicly traded on the New York Stock Exchange, and from startups to OEMs. With regard to functional safety, we are the experts. LHP holds a voting seat at the ISO 26262 table. We are the exclusive North American training partner for TUV Nord in Germany. Our technical training portfolio comes with continuing education units, commonly referred to as CEUs, from our partner IEEE. LHP is also an ISO 9001 certified company. This standard is a complex and an encompassing process, and LHP is there to guide you every step of the way. We have designed our own process called the FS Expressway to guide our customers from the adoption of the standard through the audit with your certifying agency. Your functional safety journey with LHP begins with a gap analysis to review the processes you already have in place. Not everyone needs to start from scratch. We'll review your company's safety culture, your processes surrounding product development at the systems, hardware, and software levels. The action report will shed light on the actions that need to be taken to fill the voids we outlined back in your gap analysis. Once we have a plan in place, the fun starts. This next part is where I come in. Undoubtedly, training will be in order. Your organization will need to certify engineers who will be implementing 26262. TUV Nord's 5-day intensive training session over the standard includes the examination to earn your functional safety Certified Automotive Engineer credential. Once we've jumped the training hoop, it's time to begin the implementation phase. Your functional safety manager will lead the initiatives according to the standard's guidelines. In many cases, LHP serves as our customer's functional safety manager, and we direct the work that needs to be done. Your last stop is your compliancy audit with your certifying agency. TUV Nord is one of the world's largest certifying agencies for ISO 26262. Partnering with LHP and TUV Nord can ensure your road to functional safety compliance. Thank you for listening. Now I'd like to turn the rest of the presentation over to Victor.
My name is Victor Aguilar, and I am a Solutions Architect for functional safety here at LHP. And today I'll be giving a short overview of the ISO 262-2018 standard. This standard applies to electrical and electronic systems used in serious production vehicles such as passenger cars, trucks, buses, and even motorcycles. However, it does not include mopeds or specialty vehicles such as those designed for drivers with disabilities. This figure here comes from the standard itself. It actually provides a very good overview of the layout of the standard. The standard itself is comprised of 12 parts, and what we're going to be doing today is going over each of the parts one at a time. Part 1 really focuses on the set of terms used throughout the standard. It wants to ensure that everybody has a common understanding with different terms that are being used throughout. So here's a short list of things I thought were pretty important. A common question that I get is, what exactly is functional safety? Well, per the standard, it refers to the absence of unreasonable risk due to hazards caused by malfunctioning behavior of EE systems. The keyword here is malfunctioning behavior, as the rest of the standard focuses on the prevention or detection of such behavior. Also, the standard focuses on 4 levels of known as ASO as a way of identifying the criticality of a system. ASO A is the least stringent, where ASO D is the most stringent. Part 2 of the system focuses on functional safety management. Section 2.5 really provides guidance on how to create a safety culture for your organization. Things like instituting organizational rules and processes. It wants to ensure that we have this infrastructure in place to make sure we can manage a safety-based project. Section 2 focuses on the management of an actual project now development. So this could be things like supplier management, also performance of confirmation reviews. Wants to ensure that throughout the execution of the project, the actual ISO 262 process is being adhered to. Section 2.7 focuses on management while the system is in production or in service. It wants to ensure that we not only have the proper documentation in place, things like safety manuals, but also knowing what it is that we can do in case there's things like anomalies that are noted in the field. We do things like trend analysis, information that can be used and fed back to engineering for any design improvements or evaluation of safety issues. Part 3 of the standard focuses on the concept phase at the vehicle level. Although this is really seen as the OEM responsibility, it's very important to understand, even if you do not represent an OEM, as it really sets the stage for the rest of the project. Section 3.5 focuses on documenting the actual item. It's really defining not only the boundaries, but the system's interactions with other systems. For example, my braking system and my steering system, and what interactions we have with the drivers. Once we have an item defined, the focus then becomes in trying to understand any potential malfunctions of the item, and not only malfunctions, but also identifying what are the potential consequences if something goes wrong. Once we understand the potential consequences and severity, we need to put a safety concept around it on how we're going to go about mitigating issues, or if we cannot mitigate them, how we will detect malfunctions, and if we do detect them, what are we going to do about it? So this is a little more deeper dive into the HARA portion of Part 3. In the HARA is actually a 2-step process. The first goal is to identify the vehicle level hazards as a result of malfunction behavior of a system. And once you identify your hazards, then you perform a risk assessment. So in this example, that comes from SAJ 2980. Let's evaluate the steering assist function. There are different malfunctions that can occur, such as those provided by, such as providing unintended steering or too much steering, say steering even in the opposite direction of where you're intending going. The goal is to identify which malfunctions can lead to a hazardous situation. The next step is to perform a risk assessment. The risk assessment is shown below, and it's a multi-step process in itself. First you want to estimate the probability of exposure to events where malfunction behavior will put you in a hazardous situation. For example, what are what percent of the time are we in heavy traffic or overtaking another vehicle? Next, you want to estimate severity. If the hazardous situation was to happen, what are the potential consequences? Are we talking bumps and bruises, or are we talking fatalities here? Next, you want to estimate the controllability if a malfunction was to occur. How difficult is it going to be for the driver to control the vehicle? Once you have those three factors identified, then you can calculate the ASO, as shown in the next slide. As you can see here, the three major factors, probability of exposure, severity, and controllability, have a rating. From E0 to E4, S0 to S3, C0 to C3. Once you estimate these three factors, then you use the table 4 to identify the ASO level of the system. Now, this identifies how safety critical is the system, where ASO A is the lowest safety integrity, and ASO B is the highest safety integrity. So once we know our hazards and we know our ASOs, and the focus then becomes on creating safety goals. Safety goals are really the top-level requirements that will prevent these hazardous conditions coming to fruition. Once we know our highest safety requirements, then the focus becomes on creating what is known as functional safety requirements. Again, this is now focused on preventing or detecting, and if detecting, what is it that we can do about it, and putting that those requirements and documenting them as FSRs, functional safety requirements. Each functional safety requirement carries the ASO and the integrity of the parent safety goal, and requirements are allocated to individual elements of the system. Then part 4 comes in, and we take on, and it begins, with the FSRs as the inputs, and the focus is to produce a set of technical safety requirements. You could think of the FSRs as, what is it that we want to do, where the TSRs is, how are we going to do this? It provides a lot more details on how it is that we're going to implement the safety concept, and now it analyzes the architectural design, and it allocates requirements to more individualized and specific components within the design. Since now we are in a V model development, the right-hand side of V, section 4, now focuses on verification of the safety measures. Are they properly implemented? Even higher up the V is safety validation. What we're trying to answer basic questions is, are these safety goals correct and accurate and proper for the hazardous situations that we create or that were analyzed? Now, the term system is a very generic term. It's all a matter of perspective. In a vehicle level, you can have a system that is comprised of various subsystems. Well, each subsystem should, in theory, have its own technical safety concept. You may have a vehicle level safety concept, which then, where requirements get allocated to individual subsystems, and each subsystem needs to understand and needs to know and document what it is that it's going to do with those technical safety concepts and create its own. It may lead to, further hardware and software requirements for each individual subsystem. And, then the focus on the right-hand side of it becomes, integrating these components, in a higher level as you progress down up the V cycle. Eventually we'll get to vehicle level testing. Part 5 of the standard focuses on taking the technical safety requirements and allocating specific requirements for hardware. Not only how is the hardware going to comply with the technical safety requirements, but also, focuses, a big focus of Part 5 is on the computation of the hardware architectural metrics. Hardware is known to fail, and we need to analyze and keep in mind that at some point it will fail. So we need to understand and account for that in our design. So, as part of the development process, we need to have foresight into the potential malfunctions of hardware components and categorize them. Is this fault going to be a safe fault? Is this going to directly lead to the violation of the safety code? And so the standard defines three hardware architecture metrics that need to be assessed. There's a single point fault metric, there's a latent fault metric, and there's a random hardware failure target values. And depending on the ASO level, certain percentages need to be met. The STF metric measures the coverage of the safety mechanisms and their ability to prevent hazardous conditions from a single fault. The latent fault metric reflects the robustness of an item to latent faults. And then the PMHF is really the quantitative probability of violating each safety goal due to random hardware failures. Now, Part 6 of the standard focuses on the software level development. This again takes requirements from the technical safety concept and technical safety requirements and to produce software safety requirements. Now, software is really not known to fail randomly, so the focus becomes, how do we ensure that systematic failures are not part of the system? And so it is very heavy and focuses a lot on process. And Part 6 really focuses on two major portions of the software development, the development at the architecture level and the development at the unit level. Again, since this is a V model type development, the standard focuses on verification. There are multi-stages at which software needs to be verified and tested. So this is more of a zoomed-in version of the V-cycle development of hardware, and what it's looking for, of software. What it's looking for is the development of the safety requirements at the architectural design and progressed by the developments at the unit design. And for testing, it's looking for a multi-stage testing process. Verifying the units individually, make sure that they comply with their design and their requirements. Once the units are tested, it wants us to integrate some of these units and also test that the integrated software is working as it should. Once we feel comfortable with the integrated software, then it's time to move it more for on-target testing into an actual product. And so that it's the focus of 611 is testing at the embedded software. Once we're comfortable with the software, then we're ready for integration testing with hardware and as part of the system level testing. And so as you can see, Part 6 does emphasize a lot of the rigor of the process. Part 7 focuses on preparing the system for production. Do we have the right paperwork in place? Do we have the right manuals in place? Do we have the safety manuals? To get it ready to a handoff to the service portion of the organization? A lot of the focus does become on ensuring that the proper documentation is in place, and also once it is in service, what kind of information is going to be fed back to engineering? What kind of information are we going to collect to ensure that any anomalies that are seen throughout the operation can be fed back to engineering for analysis of safety implications. Part 8 of the standard focuses on the supporting processes. These are things that are needed throughout the development that really lend itself to having a safe culture within the organization. Things like configuration management, change management. Do we have a problem reporting system? One of the areas of focus is the confidence in the use of tools, of software tools. So we'll be using a lot of tools during the development, and what the standard is asking for is, have you evaluated how the potential impacts in case one of these tools has a software bug, for example, maybe a compiler, right? If it's not a better compiler, it can potentially introduce bugs into your design. And so there's a focus for us to analyze these potential bugs and malfunctions of the software tools and see how we can mitigate that from happening, or how we can detect that from those faults. Parts 9 and 10 really provide additional guidance for Part 9 is really on the safety analysis. A lot of these safety analyses are happening throughout the design, not only from the concept level, but also in the hardware level, and this portion of the standard provides additional guidance on conducting those analyses that are ASIL dependent. Part 10 of the standard is really a guideline on using ISO 262. You can see things like examples on how you take your requirements, decompose them a little further, and also, some good best practices on how to use the standard itself. Part 11 is something that was newly introduced in 2018 version, and it's focused around semiconductors, not only on a computation of fit failures, but also how is it, that you design when using semiconductors. Do we treat it as hardware? Do we treat it as software? Or maybe a combination of both is more suitable. So those are some of the guidance they can find on Part 11. Part 12 is another part that was introduced, in the 2018 standard, and this is more geared towards the adaptation for motorcycles. The focus here really becomes on, how is it that we use the standard and tailor it to motorcycles. So it repeats some of the concepts of Part 3, Part 4, and adapts it to motorcycles. As an example, when we're conducting a HARA analysis, for motorcycles, it has something called MSOs, the Motorcycle Safety Integrity Levels. And basically what we do is we compute, or we do the HARA now and compute an MSOL. And once we have an MSOL, we use the table 6 as a translation for to an ASIL integrity level. And once we have an ASIL, then we refer to the rest of the standard to proceed with the development as described in the standard. And this concludes a very quick overview of the standard itself. Thank you for listening.
So that's it for our webinar. You will also be emailed the slide deck we used today. The final slide lists LHP representatives who can either answer you directly or connect you with the appropriate resource. Thank you for learning with LHP Engineering Solutions.